All right, welcome back. Let's pick it up. Set 4 has to do with aromaticity, aromatic compounds, benzene rings and their derivatives, and some of the reactions that go on with these. We're backing this right up against the alkene and alkyne homework set because we want you to recognize the similarities and also the differences between these. Okay. So many drugs, almost all drugs, start with benzene as sort of the building block. There's Nexium down there. Everybody knows what Nexium is. Anti-ulcer. Yeah, you better not have to take Nexium yet, and my cat better not either. All right, you don't. That's fine. Cymbalta, also antidepressant. You can see these benzene rings all over the place. So what is it about these benzene rings and aromaticity that makes them so important? It's certainly something that's involved, taken advantage of by the body a lot. So it's obviously something we better study and get to know. Some more. There's Tylenol, acetaminophen. Got that benzene ring with things attached. Lidocaine, which is one of the things that gets injected by a dentist to help numb your face whenever work has to be done. And there's Claritin for those of you who suffer from seasonal allergies. That's what that stuff is. And you can see rings and fused rings. Pretty interesting. All kinds of stuff going on there. So there must be a reason why that molecule works. Later on, we can figure it out. Okay, so what is it about these benzene rings? You can see that it's 6 members here with a hydrogen on each. The double bonds go on non-consecutive carbons. And since every single one of these is 1, 2, 3, 1, 2, 3, 1, 2, 3, 120 degrees trigonal planar, that becomes important for understanding what the generalized shape of a benzene ring is. So each carbon is trigonal planar, right? All in the same plane, 120 degrees. So it's a planar molecule. It's flat, 2-dimensional. And each of these, with whether or not the double bonds are here, and it basically is a resonance structure back and forth. You might have learned about resonance in Chem 111. It doesn't matter. The point is that this is sort of taking the sort of statistical average of both. The point is that these are equivalent. They're exactly the same. We can treat them the same, and they're all correct. Okay. So, as a way of discussing this as well, we can look at this and think about this in terms of how these work and how we describe them. And again, same arrangement of atoms, but a different location of the electrons. And if it has a different location of the electrons, but all the atoms are in exactly the same place, that's what we call a resonance structure, in which all we do is flip around the electrons, move the electrons around. Think about it. If this electron pair in the double bond goes here, and this one goes here, and this one goes here, you end up with this. And what happens with a resonance structure, that's what that means. It means it doesn't switch back and forth, but it's an average. So not a switching, but an average. And for resonance structures, I like to think of them sort of like mixing paint. Think about it. If you wanted to paint your bathroom and you had this particular wonderful color of sort of, I don't know, puke green or something that you loved. And if anybody's ever gone to Lowe's to get a custom color paint done, what they do is they, if it's puke green, it's an awful lot of blue and an awful lot of yellow and a little bit of white and a little tiny bit of black and maybe a eensy speensy little bit of pink. And then they throw them all together, they stir it up really well, and you get one color of paint, right? Just one color of paint. How cool would it be is if you got that weird color and you painted it on your walls, and every 24-hour period, it would switch. Like about 40% of the day, it would be just that original blue color. And then in another 40% of the day, it would switch to the yellow. And then for about 25 seconds, it would be all pink. And then it would switch out for another 2 minutes to be the black. And then, you see what I'm saying? We don't have things switching between. Instead, it's sort of an amalgam, a mixing, a smearing out of all the possible combinations so that there's one particular color. That's what a resonance structure is. Okay, so the actual structure is a combination of both. We could even say all the resonance structures, and they call it a resonance hybrid. Okay, and in this hybrid structure, all three electron pairs in the double bond part are delocalized, meaning basically delocalized, which means they sort of float up above and below the flat plane of the single bonds of the ring structure. So if you looked at it from the side, the electrons are sort of up here and down below. Okay? If you guys remember your things that you learned in 111 about pi and sigma orbitals, they're in the pi shell. So they're up here and they're down there. But we're not going to worry too much about that. Just to give you the idea here is that delocalization, this is the main part, gives great stability for the ring structure, and where other unsaturated hydrocarbons, which are the alkenes and alkynes that we just talked about, alkyne, oh my goodness. These guys were pretty reactive. And what we're going to learn is that benzene rings are not very reactive. Okay? So let's go with the naming right? We talked about what they are, then we talk about the naming, and then we talk about properties, and then we talk about reactions, or reactions and then properties. That's the way we do it every time with every different kind of functional group. And as you learned already on one of your early quizzes, benzene rings are considered a functional group. Okay, so the same basic rules apply once again. For a mono, meaning one substituted benzene, meaning one thing attached, you name the substituent first, then you add the word benzene because you have to get that parent chain, and the benzene ring is always the parent chain. So we look at this parent chain, add the word benzene on the end, so you know you're going to have benzene. And what is this stuff? That's a chloro group, so this is chlorobenzene. Benzene is at the end. What is this? 1 carbon, 2 carbons, so that's ethyl benzene, right? Because it's an ethyl group attached. This you better recognize at this point as an isopropyl group. So if you have an isopropyl with a benzene, you have isopropyl benzene. Not too bad, but there's a little bit more to it that we will talk about next, which is before they had the IUPAC naming system, there were some, I don't know, hundreds, maybe thousands of organic chemists that were working on different things simultaneously. There wasn't a straightforward and agreed upon naming system. And so one of the things that some of these scientists would do is common names for things. Hey, we have water, right? We don't call it dihydrogen oxide. We call it water. That's a common name. We call sodium chloride table salt. It's a common name. There are some common names for some monosubstituted benzenes, and these are used so often that you must learn equal memorize them. There's no other way around it, just because the common names are used so often. So what are the common names for these particular compounds? I know you want to look at this and call it methylbenzene. And that isn't necessarily wrong. In fact, I wouldn't call it wrong, but if I ask you for the common name, you have to recognize this as toluene. You have to recognize this as phenol. The benzene ring sometimes is called a phenyl group, and therefore phenol is sort of like a benzyl or benzene alcohol. An NH2 might be called aminobenzene in the IUPAC naming system, but you have to also recognize this as aniline because it's still used very often. A-N-I-L-I-N-E, aniline. This is a carboxyl group, and the common name for this is benzoic acid. Benzoic acid. And because this is an aldehyde group, this is a carboxylic acid group, or carboxylate group. This stuff is called benzaldehyde. Okay? There's no other way around this. You got to memorize them, okay? Because we're going to use it whenever we name them as well. And you have to be prepared for all of them, either the IUPAC names or the common names. Okay. Ortho, meta, and para only happen with di-substituted benzenes with two different groups off the benzene ring. Di meaning two. Okay, so two groups attached. You number the ring to give the lowest numbering to the substituents if you're using the IUPAC name, or you can use prefixes to show the arrangements, either the numbering or the prefixes. Ortho is whenever they're right next to each other. Meta is whenever they're one position apart. And para is if they're across from each other. So there are two ortho positions if we're looking at the first group attached. There are two meta positions, but only one para position. So the first substituent would be 1, and then this would be 2 or 2. This would be 3 or 3, and this would be 4. Okay, so how does that work with actual naming? Well, let's give it a go. Sorry. M-xylene because they're one group apart. Or there's P-xylene whenever they're across from each other. So that's certainly one way that you could name this compound with the common name, and you can see where there's some advantage to that because it's pretty simple. But the IUPAC way we'll do underneath, it's either 1,2-dimethylbenzene, 1,3-dimethylbenzene, or 1,4-dimethylbenzene. If you wanted to do numbers, and if you wanted to use ortho, meta, and para, an equivalent name is ortho dimethylbenzene. Because you know by hearing ortho that the two methyls are right next to each other. You wouldn't call that orthobenzene. Why? Because what if you had two chloros next to it? That would still be two substituents that were right next to each other, but you have to name what the substituents are, right? So this guy would be called meta-dimethylbenzene. And this would be para. Dimethylbenzene. Okay, it's not too bad. Let's more practice. Little bit more practice. I keep hitting the button too hard and going to the next slide, but we'll keep working on it. Keep getting better. Gonna try. So, di-substituted benzenes. Once again, you have to determine the parent, and that's either benzene or one of the common derivatives. Okay, we talked about all of these that you had to memorize. And if benzene is the parent, then alphabetical priority. And if the common benzene derivative is the parent, the substituent that makes it the common derivative is carbon number 1. So if you remember phenol, 1, 2, 3, 4, 5, 6 has an OH attached. So this is going to be carbon number 1, and then wherever the substituents are attached, we would do the numbering from there. And now if we're going to number alphabetically followed by the parent. And you can use ortho, meta, or para if it's a di-substituted. Okay, so let's keep practicing here. So you determine the parent. Now, that and that don't match up with any of these, right? So therefore, benzene is going to be your parent here. Now, this you know of as aniline, so that can be your parent. This you remember as toluene, so that can be your parent. Cool? Again, this is about looking at the molecule, knowing what you have to think about, and then going through the process of identifying things. After you get that parent, then you number the substituents. Now, if benzene is the parent as opposed to the common derivative, you number by alphabetical priority. In other words, you want to make chlorine C, and this is an ethyl, which is E. So you're going to decide that the chloro gets to be number 1, and you certainly wouldn't go 1, 2, 3, 4, 5, because you want to keep the numbering the smallest. And so you go 1, 2, 3. And then from there, since you know that chloro is going to be number 1, then the ethyl is in the meta position, or 1, 3 position. Now that's if benzene is your parent. If one of the common derivatives, the common name derivatives, is what you're going to use, this, because it's the NH2 that's attached to the ring that makes this aniline. By definition, that means that that's carbon number 1. And again, we're at the 1, 3 or meta positions. And here we're ortho because this is carbon number 1. That's what makes this stuff the common derivative. And then this group is now ortho. Cool. So let's continue on and finish out the naming of this. So these are the same substances that we had. So we decided that benzene was our parent and that chloro was going to be our first because the C beats the E for ethyl. And so we're going to call this 1-chloro-3-ethylbenzene. Or because you know it's a 1,3 substitution, you can call it meta-chloroethylbenzene. That does not mean that the chloro, well, you know what? It doesn't matter. Metachloroethylbenzene, when you look at it and you go to name the thing, all that means is the chloro and the ethyl are in the meta positions. The 1 and the 3 doesn't really matter whenever you write it like that, right? So again, the name to the line structure is a lot easier than the line structure to the name. 3-ethyl aniline means that aniline is what you start with, and then the ethyl group is on the meta position or the 3 position. That's the isopropyl group. Toluene is the base or the parent, and so ortho or isopropyl ortho or 2-isopropyl toluene is correct here. Okay. So let's name these guys. And what's the first job? Find the common derivative. Abby is cheering you on if you didn't, or if you heard her meow at me. Derivative. Okay. I'm hoping you're looking and you say, oh, I know what that is. That's toluene. And since this is in the 3 position, or the meta position, we can call this 3-chloro toluene. or M or meta chlorotoluene. Not too bad, pretty simple. Okay, there is no common derivative here. So now we just have to call this what it is. 1, 2, 3, 4. So this is 1,4-dichlorobenzene, because benzene ring is the parent. Or you can also call this para-dichlorobenzene. Nice, not too bad. What's the common here? The common is phenol. And this is ortho or 2-chloro substitution or substituent. And so you can call this 2-chlorophenol or O-chlorophenol. Got it? Good. Let's practice up, be good at it, be able to do it on your own, and let's try maybe one more. Oh, we already did the numbering system here for each of these. Good. All right, so what's the name of this thing? Well, do you see a common base? A common parent? I do. I see that. I see that as phenol. We just did one like that. Could this be right? Para-hydroxybenzene? Where's the bromo? Huh? No, that can't be right. Anisole, I don't know what anisole is. I think we might look at anisole later, but we haven't learned that yet. And is that a methoxy group? We don't even know what a methoxy group is, so that can't be right. So it's either going to be para-bromophenol or meta-bromophenol. And para is a cross. And it's not a cross. It's at the 1, 2, 3 position, and that's why meta-bromophenol is right for this guy. Excellent. Let's move on. Continuing on with polysubstituted benzene naming system problems. Remember, determine that parent. The parent is either going to be benzene or a common number to give the lowest possible numbering around the ring. This is for polysubstituted benzenes, many. So not just 2, but more than 2 are attached. So you number to give the lowest possible numbering around the ring. And if we're going to use the common derivative, remember that means that that guy is always carbon number 1, whichever one makes it the common derivative. But you don't ever have to say the one. Why put more things on a name than you have to? And then you name the substituents alphabetically, followed by whatever the parent is. Because it's poly, you can't use ortho, para, or meta because there's too many spots. Okay, so again, the words or the explanation or the steps to naming is a whole lot more to write out and talk about and think about than the actual doing. So let's do some actual doing, shall we? Good. All right, so we're looking here. Benzene could be the parent if you want to go IUPAC. Or you could look at this and decide, oh, the parent is phenol. Do you see anything that is like a parent on this guy that's one of the commons? I say no. No common group. There's no OH or NH2 or carboxylate or aldehyde or methyl. None of those. And so benzene is going to be our parent here. Excellent. So once we've the parent is, then the next step is number to give the lowest possible numbering around the ring. Since we've decided that phenol is the parent, that carbon has to be carbon number 1. And if we went in this direction, that would be 2, 3, 4, 5, 6. And clearly 3, 6 is not nearly as good as 2, 5. And for here, for this guy, since benzene is our parent, this is chloro with a C. This is isopropyl. And we remember that's a special, so that's an I. And this is ethyl with an E. We would want to start with 1 for the chloro, and we certainly wouldn't go this direction, 2, 3, 4, 5, 6, because 5, 6 is worse. So that's why we're going to go 1, 2, 3. Okay, so we've got a 2 isopropyl and a 3 ethyl. Over here, we've got a 2 chloro and a 5 bromo. Okay, so now that we have the numbering system down and we know what the parents are and we've counted what the substituents are, let's put the thing together. Okay, so if we have 2 chloro, the 1 is related to the phenol part, and 5 bromo, what comes first? Alphabetical. So we've got 5 bromo, 2 chloro, phenol. That's it. Over here, since benzene is the parent, we're going to end up with a benzene. And what is it? Well, what comes first? C, then E, then I. So 1 chloro, followed by 3 ethyl, followed by 2 isopropyl benzene. Okay, that's it. Not too bad. Just follow the rules. Know the rules, remember the rules, follow them, practice them. Next. Sorry about that. Benzene is the common, or the parent. Okay, so this is ethyl, this is propyl, and this is chloro. We're clearly going to put the 1 on the chloro, and I think it's obvious that we're going to count like this. So we've got 1 chloro, 4 ethyl, 3 propyl, benzene. That's it. Not too shabby, not too bad. Remember, it's not putting the substituents on by number. It's putting them on by alphabetical priority. Okay, practice, practice. So what do you think? What's the name of that sucker? Ooh, I see a common, because that's a methyl group. That is toluene, right? So that means that's carbon number 1, 3, 4, 5. So I'm thinking 3,5 dichlorotoluene. Now, why wouldn't you use meta? Because we don't use meta for polysubstituted. And it's not 2, 4 because that's 2 and that's 4. And this, while not being, well, no, that won't work. Look, methyl chloro, 3-chloro, that doesn't work. We have to use dichloro. There's only one that works here. Number C. Good. Sorry about that. They're resistant to many reactions. Certainly anything that breaks up the aromatic ring part, they're not going to want to do. However, they are very flammable and volatile, just like every other hydrocarbon. Okay? So, because we know we don't want to break up the aromatic system, these do not undergo the addition reactions that characterize alkenes. It's easy to make this stuff react to add on. Okay, that's easy to do. But whenever we have an aromatic system, this is stable, therefore doesn't want to add because it does not want to break up the ring. Think about it. Whenever we react Br2 with this double bond, what do we end up with? Single bonds. If we added in the same way, we would break up the double bond, and then we would no longer have the aromatic system, which is extra stable. So that's not going to happen. And man, if you can start to think about these molecules and think in terms of what's stable, what's not, what will want to react and what won't, that will really help you a lot. However, as we will see shortly, there are some reactions that can go on. Let's see what those are. They don't undergo adding and losing the aromatic system, but they will substitute something that's hanging off the benzene ring. Remember, every benzene ring has a hydrogen attached at every carbon. And what we can do is undergo a substitution reaction. In which we substitute one atom, which will be the hydrogen, with another. An atom is replaced by a different. Like in this case, the X gets added on instead of the H, and then the H jumps on to hang out with the Y instead. It's a substitution of X to where the H was. And the main reason why that happens, and the way we're going to make all these different drugs, is we keep that stable aromatic ring intact. And we'll find out that the X can be halogens, X can be nitrate, X can be lots of different things, and we'll talk about those shortly.